Yeah, that's blot here, so it's really probing basically the earliest structures we know in the universe. This kind of data comes in a fraction of the time that we were before. So I think a lot of the records that we have in the current-day universe, those are going to be broken really soon. A well-known Nobel Prize winner says that the James Webb Space Telescope has just found something strange in the universe, and the changes that are coming may not even be ready for us. The most recent findings are very bad for science. More and more crazy things are happening because James Webb has found a brand new effect that is turning our physics books on their heads. Adam Reese, an astronomer and Nobel Prize winner, has long thought that science is on the verge of disaster. There are piles of unsolved problems that are getting bigger every day. According to researchers, can we still figure out what's going on? Or is the field of science over? Adam Reese is likely one of the few experts who is staying calm these days. Things are not the same as they were before the James Webb Space Telescope was launched. It's likely that the universe is much older than we thought. Galaxies have formed much faster and in very different ways than we thought they would, and the universe may not be growing from a single point. What should we do now if dark matter was just a mistake and James Webb is already showing us the next picture of strange things happening in the universe? One of the most knowledgeable people in the area of studying how the universe is expanding is Adam Reese. His work on finding that the universe is expanding faster than we thought changed the way we think about the universe and was a big part of the Hubble excitement. Because he has worked hard for decades, Reese knows that our understanding of the universe is wrong, so he is excited about what the telescope has found recently. He helped look at the universe and used supernovae as standard candles for the first time. In this way, scientists use cosmic scales to measure how far things move and how fast they move. Standard lights are a lot like those using supernovae as standard measurements, which were amazingly accurate. But there was still one problem. Reese and his team discovered that the universe was expanding in some areas more than others, which was not what they thought would happen during their work. Something else became clear. Reese's measurements were very different from those based on the redshift method, which shouldn't have been the case. The Hubble strain is what we now call these differences in the measurements. Their work was so great that Reese, along with his co-workers Saul Perlmutter and Brian P. Schmidt, won the Nobel Prize in Physics in 2011. It turns out that he won the award for finding that the universe is expanding faster than usual. Schmidt and Reese are both part of the High Z Supernova Search Team, which is looking into ways to improve how far things can be measured in the universe as part of the Supernova Cosmology Project. Perlmutter, on the other hand, came to the same results around the same time. They saw type Ia supernovae, which are very bright stars that explode and are a good way to figure out how far away things are in the universe. These findings surprised everyone by showing that the rate of expansion of the universe is going up, instead of down as was thought before because of the gravitational pull of matter in the universe. The isotropic universe was a bad idea. It was building up to be the biggest problem in modern science, and now it's happened. These days, scientists and cosmologists are always being given new questions and shocking facts. Now the idea of an isotropic universe is also about to fall apart, taking with it one of the most important parts of our cosmos. No matter what way you look at the universe, isotropy says it looks the same. A fundamental part of the cosmological principle says that if we look at the universe on a big enough scale, it is uniform and has no different areas. For instance, the pattern of cosmic microwave background radiation seems to be the same everywhere. Also, big groups of galaxies are spread out almost evenly in space, or at least that's how it looked in the past. Scientists then turned these observations into simple math rules to make it easier to explain the world, but this could have been a very bad idea. Adam Reese and other scientists studying accelerated expansion first proved the isotropic model, at least in part, because measurements of supernovae had shown that the rate of expansion is always the same. That is, it looks like there is some kind of isotropy. However, the growth is happening a lot faster than old physical ideas say it should. The end of dark energy science is still very interesting right now. We need to learn more about dark energy in order to figure out the new cosmology's puzzle. We still don't know what this energy is made of, but knowing that it exists and what it does is important for understanding how and why the universe grows in a way that isn't skewed and how the current standard model of cosmology came to be. Dark energy is an idea for a type of energy that might exist anywhere in the universe. It is likely a key part of the current theory about how the universe is expanding. It is thought to be the force that is pushing against gravity and speeding up the growth of the universe. It spreads out the universe. According to the current idea of cosmology, dark energy makes up about 68% of all the energy in the universe. There is already a problem here. Scientists say that an energy that has never been proven to exist is responsible for almost 70% of the energy processes in the world. The observation of Type 1a supernovae by Adam Reese and his colleagues was a key part of the case for the presence and properties of dark energy. Up until now, the fast expansion seen here could not be described without a strong force pushing against it. The cosmic microwave background radiation and other large-scale structural studies have shown that this mystery energy is truly real, but new findings made by the James Webb Space Telescope have made people question the idea of dark energy. The JWST can look at the early universe with more accuracy than was possible before. The standard model of cosmology says that structures and objects should be younger and less developed than they were when the first detailed observations were made. It's possible that these findings show that the universe may have started earlier or expanded even faster than was thought before. All of these findings show that we still don't fully understand some important cosmic elements and forces, such as dark matter and dark energy. This could mean that the normal model of the universe needs to be completely rethought. That's not ready for us yet, though. We can't come up with new theories because we don't know enough about what's new. Will the world of quarks hold the answer? We will have to wait a little longer for the change in the way we see the world. We won't be able to put together a new picture until Webb sends us more pictures and scientists find even more amazing things. It might take a while. For now, researchers all over the world are looking for solutions that are already out there. David Gross is another scientist who is glad about the problem and sees it as a chance. Gross says that the solutions to the universe's big questions are not hidden in the big picture but in the little picture. A well-known theoretical physicist who knows a lot about string theory and the idea of strong interactions, he is also a Nobel Prize winner. In 2004, he won the prize for finding asymptotic freedom in the theory of strong interactions. The finding was very important for learning about how quarks behave. Quarks are the building blocks of protons and neutrons. The normal model of particle physics is based on these particles, which are the building blocks of everything we can see and measure in space. Because of this, the basic structures and rules of the macrocosm must also exist in the subatomic world. Among other things, Gross helped to come up with ideas about what happened right after the Big Bang. Back then, there were no stars or other things in the world. For hundreds of thousands of years, there was only a very hot primordial soup where particles could move around without sticking together. It's likely that before the Big Bang, there was only a type of quantum fluctuation where all forms canceled each other out to the point where they were physically equal to zero. This quantum fluctuation broke apart with the Big Bang. Particles full of charges and forces shot into a space that wasn't there before. In the end, these bits turned into galaxies, planets, stars, and living things like us. Should we believe Gross when he says that these particles hold all the answers? Most likely, yes. But how can we study how particles behaved 13.8 billion years ago when they were in space? The microwave background energy from space is one thing that researchers use. This is thought to be a pretty good description of what happened right after the Big Bang, and it has probably changed much since then. Quantum physicists and classical physicists don't quite agree on how to understand this record of the early world, though. In the world of science right now, quantum and particle physics and standard cosmology can't be put together. Quantum physics doesn't agree with what we know about matter, or rather, the missing link is quantum physics. David Gross is sure that this bridge can be found in particles and forces that we didn't know about before. He was one of the experts who worked hard to get people from different fields to agree on something before James Webb started the debate. He worked hard to connect quantum physics and general relativity, which he co-authored so that they made sense together. He wanted to bridge the gap between these two scientific fields. Gross's work on asymptotic freedom shows how quarks act when their energies are very high. This is very important for understanding the early world right after the Big Bang when energies were very high. His ideas can help us understand parts of the expansion of the world that we don't fully understand yet. That being said, there is some disagreement among scientists because many traditional physicists think that string theory's ideas are too hard to believe. David Gross thinks that the quantum fluctuations in the microwave background hold the answers to all the questions that haven't been solved yet. It's called the cosmic microwave background, CMB, and it can be found everywhere in the world. From 1989 to 1993, the Cosmic Background Explorer satellite was in orbit. It was the first to notice small changes in the radiation's temperature. The Wilkinson Microwave Anisotropy Probe looked into these changes from 2001 to 2010 to see if they showed proof of the Big Bang. The Planck satellite just recently made one of the most thorough maps of the CMB, but researchers are still not sure how to analyze this data. Some scientists say they have found proof of the Big Bang in the CMB, but others think it shows collisions with other universes and the presence of a multiverse. The exploration of the early universe is no easy feat, and as more data comes in, it increasingly challenges existing theories. Scientists working with the James Webb Space Telescope, JWST, are uncovering new clues that seem to contradict the long-standing understanding of cosmic evolution. One key area that remains a mystery is the nature of dark matter. For years, physicists have believed that dark matter is responsible for providing the unseen gravitational pull that holds galaxies together. However, recent observations made possible by the JWST suggest that dark matter may not be as ubiquitous or as influential as once thought. The findings from JWST have also begun to reshape our understanding of the cosmic voids that exist between galaxies. These voids were once believed to be empty regions of space, lacking in matter. However, new observations are starting to show that these voids may not be completely devoid of matter, but instead contain hidden structures and subtle forms of energy that are not detectable by traditional means. This could significantly impact our ideas about how the universe is structured on a large scale. Another ongoing puzzle is the role of black holes in shaping the formation of galaxies. While black holes have long been known to exist at the centers of most galaxies, the exact relationship between these supermassive objects and the galaxies they inhabit is still not fully understood. Some theories propose that black holes play a critical role in regulating the growth of galaxies, while others suggest that their influence is more limited than previously thought. The observations made by JWST could help clarify this issue by providing a more detailed look at the environments around black holes, particularly during the early stages of galaxy formation. As these new discoveries unfold, scientists are increasingly turning to computer simulations to help make sense of the data. These simulations attempt to recreate the conditions of the early universe and explore how various forces, such as gravity, dark energy, and radiation, interacted to shape the cosmos. By comparing these simulations to the actual observations being made by telescopes like JWST, researchers hope to pinpoint the factors that have led to the current state of the universe. One of the most exciting prospects in the field of cosmology is the possibility of discovering entirely new forms of matter or energy. For decades, scientists have speculated that there may be more to the universe than what we can currently detect. Whether this means discovering new particles, forms of radiation, or entirely unknown forces, the potential for groundbreaking discoveries remains high. As technology improves and more data is collected, researchers are optimistic that they will uncover secrets that have remained hidden for centuries. The emerging revelations from the James Webb Space Telescope are also challenging the very foundation of cosmological models that have been in place for decades. One of the most perplexing questions being raised is the potential for multiverse theories to find support in the data. The idea of a multiverse, suggesting that our universe is only one of many existing in parallel, is a controversial and speculative concept in physics. However, some recent findings, such as anomalies in the cosmic microwave background, CMB, radiation, are causing scientists to reconsider the possibility that we may not be living in a singular universe but part of a much larger cosmic structure. Furthermore, the concept of cosmic inflation, which posits that the universe expanded exponentially in the first fraction of a second after the Big Bang, may also need to be reevaluated. Some of the observations from JWST suggest that the initial moments of the universe may have been even more complex than previously imagined, with possible fluctuations in the rate of inflation or even multiple inflationary events occurring in different regions of space. If confirmed, this could drastically change our understanding of the birth and evolution of the universe, suggesting that inflation may not be a universal phenomenon but something that occurred in localized regions, giving rise to various pocket universes. Another key development is the progress made in understanding the early formation of stars and planetary systems. JWST's ability to peer deeper into space than ever before allows astronomers to witness the formation of these celestial objects in unprecedented detail. Observations are revealing that stars may be forming in ways that deviate from current models, indicating that we still have much to learn about the processes that lead to star birth and the conditions that make life possible in the universe. As these mysteries unfold, the scientific community is entering a new era of discovery, one that promises to redefine the boundaries of what we know about the cosmos and our place within it. The questions raised by these findings are only the beginning of a journey that may uncover even more astonishing truths about the universe.